So a friend of mine tells the story of learning English as a second language in her home country before moving to the United States. And as you'd expect, she learned the very formal way of greeting people with, "Hello, how are you?" Probably from a cute little textbook like this that we're all used to. So imagine her surprise when she comes to the US and hears people greeting each other, even in semi-formal settings, with "Hey there," or "Hey," or "What's up?" So it certainly took some adjusting for her. And I think we've all encountered this phenomenon that I call the "what's up" problem, where there's a disparity between what we've learned in school and what we encounter in the real world. And even technical subjects such as data science and machine learning are not immune from that, despite being what you would think of as fairly objective, math-centric, straightforward fields. And I think the reason for this disparity, particularly in analytics, is that we spend most of our time learning the algorithms, the statistics, the data preparation steps, all the stuff that is really exciting and that we're all pretty passionate about. And we spend much less time, if any, on the processes that happen before you actually get data and solve the problem. And this is where things can go wrong. So if you think of problem solving at a very high level as, let's say, these 4 steps: understanding the problem in a business context, formulating it mathematically, finally solving the problem with data, and finally applying the solution. And I didn't draw a feedback loop on here, but it's of course an iterative process. I think you all will agree with me that the analytical techniques that we all love and try to master as we learn them really falls into that third box. And again, we spend very little time on those first 2 boxes. So in this talk, I don't want to talk about technical issues like sampling bias or spurious correlation or using mean squared error if you have asymmetrical penalties. Those are all very important topics, but those are topics that I really think fall in that third box. Rather, I want to focus on the softer human kind of process-related issues, and the ones that really can trip us up the most and can cost companies lots of wasted time and effort if we don't get them right. So I want to cover 3 categories of failures today. 1, not identifying the real business problem within its context. 2, not selecting the right modeling methodology. And 3, the great party platter of organizational failures. There are so many of those. So let's start with the first one. Not identifying the real problem. And what I mean by this, I'm differentiating between the data problem, where we're trying to figure out what is the appropriate algorithm, what data we need to get. Here I'm talking about the real business problem. What is the underlying business problem that you're trying to solve? And more importantly, what will move the needle? What will have return on investment for your business or organization? As data scientists, we are often asked to take a data set, start looking at it, and hey, try to find some nuggets, some insights. And then hopefully there'll be something actionable out of that. And this has always felt to me like the wrong order in which to do things. And it kind of reminds me of the old joke of the guy who lost his keys and is looking for them under the street lamp. And when somebody says, "Is that where you lost them?" he says, "Well, no, but that's where the light is the brightest." And if you kind of follow that same logic of starting with a data set and then kind of going on a fishing expedition, that's essentially what you're doing. And you're kind of hoping that when you find something, if you find something, it will be actionable and useful for your business. And so this just feels backwards. Now, this is not to say that having insights into your customer base, understanding historical trends, and being very familiar with your data sets is a bad thing. On the contrary, it's absolutely vital to your business or your organization, and it forms the core of what we call descriptive analytics. But for a data science effort to be successful, you really first have to figure out what the business needs. Otherwise, how do you know what data to go look for or collect? And how do you know that, if successful, that you will be able to kind of move the needle? So this is certainly easier said than done. A lot of businesses and organizations have clearly articulated goals and metrics by which to measure those, but a lot of them don't. But either way, this is really the right place to start. As common sense as this sounds, we see failure to follow this process all the time. And we saw it at an e-commerce company recently where there was a production database that contained information about the company's millions of customers. And since this was a production database, it needed to, it was also used, it was mainly used to make decisions about those customers when they came to the website. Those decisions needed to happen in about 20 milliseconds. So a Couchbase system was designed and built, and they used key value pairs so that when a customer came to the website, they could quickly look up everything that they knew about that customer. And not surprisingly, the data scientists at that company, after a few years, said, wow, that's really valuable information, and that's something that we'd love to get our hands on. And the production database was the easiest way for them to get that information. They could have gotten it elsewhere, but they said, we basically just want to get our hands on that. A very reasonable ask, right, from some data scientists. But the problem was that the key value store design was not set up for the types of queries that these analysts would need to make. Not only that, if they started pinging the database for all of their research purposes and analyses, it would threaten the latency requirements of this production database. So an engineer thought, well, hey, let's build a copy, a second version of this production database. We'll call it the offline database, and the data scientists kind of just can dive right in. And everybody loved the idea. And discussion started immediately around, should it be a one-for-one copy of all of the current customers? Somebody said, well, maybe it should be a superset and we should bring in all of the dormant customers, the historical customers. Somebody said, well, maybe it just needs to be a sampled subset. So how do we sample? But the step that was completely skipped was having the discussion about whether the time and effort to build, test, and maintain this second database would be worth the revenues that it would bring in. You know, what were the uses that the data scientists wanted it for? Were those things monetizable? And were they monetizable enough that it would make sense? And maybe there was another way of achieving it, right? Could they just take a weekly or monthly snapshot of the production database and give the data scientists data that way? None of those conversations happened, unfortunately. In fact, a senior engineering leader who was really excited about the project said, let's just build it, and I'm sure we'll find tons of uses for it. Now, keep in mind, this was not a research or academic institution that kind of has the luxury to play around with stuff. This was an e-commerce company in a very competitive industry that was actually at the time struggling for survival against some really serious competitors. And yet nobody in the engineering group was in tune with the company's larger goals. And they were really ready to spend about $3 million in hardware and man hours to build a system that nobody really could put a value on. So I think the lesson in this particular example is to really think about your problem. As data scientists, we want to dive right in, we want to start the modeling. But I think it's everybody's responsibility to kind of take a step back and say, will we be moving the needle? And is this really the right way to go about achieving the business goals? Okay, so let's say you've avoided failure number one, you've done your homework, you have asked all the right questions, you have talked to all the stakeholders, you know what you want to do with your analytical project. So what's the next step? Problem formulation, right? Well, now you have to watch out for failure number two, which is not selecting the right modeling methodology. Now, I assume that most of you will think that here I'm talking about using decision trees instead of support vector machines or neural nets instead of regression. Rather, I'm talking about the concept that data science is much more than just machine learning. In my mind, data science is not new. Sure, that term, that phrase is a very recent one, and one that gets used interchangeably with machine learning and predictive analytics, predictive modeling all the time. But there's really a rich history of analytics and modeling as far back as humans have been collecting data. So I won't do what the textbooks do on page 1 and go back to what the Sumerians did. So instead, for an example, we'll go back to the ancient times of the 20th century. And some of you may be aware that during World War II, the British developed operations research, which is a discipline that uses advanced analytical techniques to make better decisions. And they used, part of operations research is a subfield of math called math programming. Or have people heard of math programming? Show of hands. Yes. The OR master's or PhD. Yes. And so they use this type of math, of modeling, to make, to be more efficient in with their wartime activities, aircraft flight routes, troop deployments, figuring out how to move supplies from one place to another. And this math programming, which is one of the technologies used in operations research, is a really fantastic way of solving complex optimization problems. You essentially have you formulate an objective function of what you're trying to do, and you're either trying to maximize it or minimize it. And then you have a set of constraints that you would like to honor. And you can either specify that those constraints be hard constraints, meaning this cannot be violated, or you can say to the computer, hey, try your best to meet this constraint. And if you can't, you might incur a little bit of a penalty. But it's a wonderful way of formulating complex, multi-objective types of problems. And it's actually a type of math that is still widely used 80 years later by the airline industry, a lot of manufacturing settings, and even a lot of non-industrial applications. I recently read a paper where the NFL was using it for optimal game scheduling, which is kind of cool. So other than that example, there are also well-established techniques to deal with lots of different types of analytical problems, queuing problems, figuring out the reliability of components, simulation, dynamic pricing, inventory control. And I would argue that a well-rounded data scientist is at least familiar with all of these techniques. It's obviously a very tall order to be proficient in all of them. But at least if you can recognize when you see a problem what the best technique is to solve it, you will avoid some costly mistakes. Now, it can certainly be tricky to know which technique to use when, and sometimes even the wording of the problem can kind of point us in the wrong direction. So suppose you are asked to predict the amount of time before this component fails. So say somebody is trying to come up with a reasonable maintenance schedule for, say, a fleet of aircraft. You see the word predict, your mind immediately kind of goes to predictive modeling, when really this is kind of the classic problem that can be solved using techniques of reliability theory. Similarly, you might get asked to predict the average number of minutes that a bank customer will stand in line. And again, that word predict kind of makes you think about going and collecting historical data and fitting a model, when this is a problem that can be very aptly solved using queuing theory, which often goes hand in hand with simulation. Now, could you solve a failure prediction problem or a queuing problem with machine learning techniques? Sure, you absolutely, maybe not absolutely, you could give it a try and no doubt get somewhere. But my point is that there are well-established techniques way before random forests were invented, way before gradient boosted trees were invented, that have been very successfully applied to these types of problems, to specific types of problems. So again, hard to be proficient in all of these, and some of you may say, hey, we're at a machine learning conference, right? It is literally in the name of the conference. And I agree with that. And yet, a lot of us call ourselves data scientists. And even if you consider yourself a machine learning practitioner, end of story, I think there's still great value in recognizing the types of problems that machine learning are not well suited for, right? The old saying of, to a little boy with a hammer, the whole world's a nail, right? You don't want to be that little boy with the hammer. So if you do make model formulation, problem formulation mistakes, they can be very costly, as my next example illustrates. You'll see, by the way, that unlike the examples we just talked about, this particular example is one where a machine learning approach would actually have been more appropriate than the math programming approach that the data scientists chose. So this was for a manufacturing company that had the problem of estimating inventory in the future. And they built this complex model to do just that. And right, sorry. If they couldn't, so the buyers wanted to be guaranteed a certain amount of inventory. The manufacturing company wasn't guaranteed to get all of the resources. It was a variable resource. They weren't even sure that they were going to be able to get everything that they asked for. So when that time came, if the company couldn't deliver the inventory, they would lose money and probably a little bit of reputation, take a hit to their reputation. If they had extra inventory, that was less of a problem, but they would incur extra storage costs. So the problem involved forecasting the amount of inventory that could be guaranteed at different points in the future, days, weeks, months, for a set of customers that would all be buying from the same pool of inventory. So the analytics group in the company decided that they decided to formulate this as an allocation problem, meaning that they would use math programming to solve it. And this was a very reasonable thing because you can think of it as allocating all of the buyer's requests to all of the inventory that you're going to have. And this, again, is just a classic problem that can be solved with math programming, in this case, a linear program, to be more specific. But now pricing came into the picture. So buyers wanted to see how much inventory they could be guaranteed for a range of prices so that they could make the best decision for them, consider that trade-off. So now the analysts said, okay, well, we're going to solve the math problem at every single price point. So, and they picked 25-cent intervals for a range of about $20. So now all of a sudden, instead of solving one math program, they're solving 80 for one scenario. But the complexities kept piling on. Since they're doing the allocation in the future, they need to feed the math program lots of forecasts of certain factors. For example, how much expected min and max inventory are you going to have in the future? Or what's the expected mix of inventory? So they fed that to the math program. By the time all was said and done, the formulation was just this monster math program. And they threw the most powerful commercial optimization software at it, leveraging high-performance computing. And even then, the solution, the whole system was sluggish at best. But at least the answers were accurate, right? Well, then we walked over to the operations people, and these were this was the department that was responsible for interacting with the clients and selling the inventory. And they had been involved in the original design of the system, the requirements. So the analytics group had not fallen into failure one. They had certainly planned what needed to be done, talked to all the stakeholders. But we then went to those ops people and said, how much do you use or depend or trust these forecasts from this highly sophisticated forecasting system that the engineers build for you? And these were some of the answers that we got. So one was, well, I'll take the inventory forecast and chop it in half. Somebody else said, well, I'll take it as a starting point, and then I'll look up and see what we did for that client in the past. Wow. So it became obvious that this highly sophisticated system. This company had spent millions of dollars over multiple years designing and building this highly complex system that the end users didn't really use. So one suggestion we made was to scrap the allocation system entirely and go with a machine learning approach. After all, there was plenty of historical data on which to glean patterns, and at the very least, it would be much simpler. The current system had about 8 to 10 engineers full-time maintaining the system, and about 2 mathematicians kind of tweaking the formulation. So about a dozen people solely dedicated to the system, whereas you can imagine building a predictive model that would require, one person to maintain. But unfortunately, the company had invested so much money and so much time, and the people who had designed it, formulated it, really dug their heels in that it was the right approach, that no alternative was ever seriously considered. So, and they kept throwing good money after bad. And it was a sad thing to see. And yet I think it's a lesson that resonates with all of us. How do you know when to cut your losses? How do you know that success is not right around the corner, right? It's kind of a tough thing. So I think the lesson is don't anchor yourself to one technique too early or too fanatically. And certainly we get back to that iteration step where really early on you want to iterate and try lots of different things. Now, some could argue that in the example I just gave, there were also some organizational failures, right? It's like you don't have to be very technical to recognize the disparity between what the engineers are saying, this is a fantastic, this is the crown jewel of our tool set, and then the ops people going, yeah, it's okay. And I think that that's a fair point too, that there were organizational failures in this particular instance. And so that leads me to our third and final failure, at least for today, and that is not structuring your organization to be successful at analytics. And so if we take a look at the following org chart, this was for a software company that was in an industry that used data quite a bit. So it was not surprising to see people in analytical roles in all departments of the company. So you see kind of the C-level, you see the engineering team, the ops team, the sales team, the product team. And in each one of those were people that had some sort of analytical role. But what's missing? There's really no centralized leadership, is there? There's no one person that can give clear direction on data strategy and who can coordinate data initiatives across the organization. And that lack of leadership became really apparent when the company was considering getting a new data set. There was a new data set in the market, and the chief product officer said, we've got to have it. This will, if our customers know we have this, it will really differentiate us from our competitors. And the sales guy agreed, right? Salespeople want to make sales, and he said, just tell me when I can start marketing this and saying that we have this. In the ops department, the senior director of data services was responsible for negotiating contracts with the data vendors. So she said, sounds good to me. I guess I'll start negotiating the contract. I'm not quite sure how hard to negotiate, what we're worth, what we're willing to pay for this data set, but I'll do my best. In engineering, the director of the big data team, who was responsible for ingesting the data, said, sounds good to me. Give me the integration specs. I'll move the work to the top of my queue, and we can start ingesting it whenever we get some sample files. And then the VP of Advanced Analytics, where most of the data scientists sat, said, okay, well, I'm not quite sure what information we'll get out of this new data set that we don't already have, but it'd be great to see some sample data, et cetera. And so the conversation really kind of devolved into everybody not quite knowing, very aware of their own responsibilities if this data set were to be acquired, but not quite sure why we were doing this. And I think this is where the role of the chief data officer comes in. So this is a fairly new C-level designation that's sometimes also referred to as Chief Analytics Officer or Chief Data Scientist, but the intent is the same, no matter what the name is. It's really giving data strategy a seat at the table at the C-level. It's elevating data really to the highest level of the organization. And so how many CDOs are there? Well, New Vantage Partners did a survey and of Fortune 1000 companies. And back in 2012, of the ones who responded to the survey, 12% had chief data officers or a similar job title. Only 6 years later, the number had risen to 63%. So huge, huge increase. And that number obviously is only still growing. And I'm in the camp that firmly believes that a chief data officer or chief analytics officer, whatever you want to call them, is absolutely a vital role in any organization. And when we think back to the examples that we just went over in this talk, you kind of think about how a CAO would have helped in those scenarios. So failure one was the e-commerce company, right, that was thinking about building the second version of the database. A CAO, I think, would have very objectively said to the engineering team, justify this, explain to me what we're going to get out of this, and I'll sign off on it if there's value in it. In the second example, the manufacturing company, doing the forecasts, hopefully a CAO would be objective enough and to say, you know, we've been trying this for a long time. It's time to start something else, to try something else. Or even better, at the very beginning, they would have enforced some sort of process and culture around, let's iterate, let's maybe explore different model formulations, show me 3, and then let's discuss the pros and cons. And then finally, of course, in this last example, a CAO would have said, what will we get out of this data set? And maybe the PR value is enough. That's quantifiable. Maybe that's absolutely enough reason to get a data set, but at least to know the reasons why you're doing something, to quantify the value of a new data set. So we've talked about 3 types of failures that can cost companies lots of time and money. So what are the takeaways? What have we learned other than kind of all cringing a little bit at these examples? So I would leave you with these thoughts. One, you really need to outscope to identify the real business problem. Don't just start with a data set and kind of go on a fishing expedition. 2, consider analytical techniques other than machine learning. Know when machine learning is not quite the right thing. So take a little bit of a broader view of data science. And finally, 3, let's try to, whether you're an executive or a data scientist at whatever level in the organization, let's try to structure our organizations to be successful at analytics. So I'd like to leave you with a quote that I really like from Bruno Aziza, which is, "It's the soft stuff that's the hard stuff." Thank you so much.
You good to take some questions? We have some time for some questions. Do we have mic runners? Yep, we got one there, and I think there's one over there somewhere. If not, if you can wait for the mic. Any questions? Raise your hands. There's one right up there in the back corner.
So referring to the second point or the second takeaway that you made, how would you say that analysts or data scientists can be more aware of the conventional techniques that we can refer to before moving on to machine learning or other advanced analytics?
Yeah, that's a good question, and I didn't know how controversial my thesis was going to be. That data science is really I take a much broader definition of it. In terms of how people can learn some of those other techniques, one would hope that data science programs that are becoming more and more common can maybe have a class not just on understanding the problem, but also on problem formulation, and at least expose people to some of these other techniques, even if it's not like super in depth. And then frankly, I mean, I think most of us are self-taught and continue the learning process all the time. And so if a data scientist were to say to me, what's the single best thing I can do to become a more skilled data scientist, I would say instead of diving even deeper into an existing technique, I would say take a step back and at least, again, be familiar with some of these other techniques. There's a wonderful conference that informs well, there's a series of conferences that the Society Informs does, and there they do cover other operations research and as well as other types of optimization problems. So it's a matter, I think, of seeking out the information.
One more question? Right here, Kenneth. Thanks.
Hi, thank you. What role do you think that the analyst or data scientist should take when seeing maybe some of the dysfunctional decision-making that's going on within the organization? Do you think it's a matter of them speaking out more? What do you think? What's an effective, I guess, intervention that you've seen that role take?
Yeah, that's a great question, and that's something that I've struggled with myself. I think first, just being aware if you are either applying to an organization that doesn't have kind of that centralized leadership, again, whether it's a CAO or a director of analytics, whatever the title is, I think you should be at least aware that you will run into some of those difficulties. It's kind of inevitable. In terms of how proactive you want to be, you could make the pitch that they need a CDO or a CAO and that you're well suited for the job. Other than that, I think it's without that leadership, I think it's everybody's responsibility to ask some of those harder questions. And if you're a data scientist on a team and you see everybody going the machine learning route, say, hey, wait a minute, guys, are we sure that this is not something that could be solved with queuing problem, or is this a dynamic pricing problem, et cetera? So.
All right, thank you. Please
Yes,
give a round of applause for Antonia.